Today's goal is to evaluate our 6 trig functions using only identities, a whole bunch of them that we're going to learn in just a bit. The plan for the video is to split it into 2 main halves. So in the first half, we'll derive our first round of trig identities, but instead of just writing them down and moving on, I'll be explaining where they actually come from. After we've made it through all the identities, we'll look at 3 examples of how you can actually use them to find trig values. There's a lot of material here, so I'll try to keep my explanations brief. This first set of problems is just a warm-up asking us to evaluate these trig functions without a calculator, so I'm going to draw out and label a 30, 60, 90 triangle. So now sine of 30 degrees just means from this 30-degree angle I'm looking at opposite over hypotenuse, which would just be 1/2. And then number 2 asks us to find cosine of 60 degrees. So from the 60-degree angle, cosine would be adjacent over hypotenuse, so that would be 1/2 over 1 again. And so you see that we got the same value here. This set is a little bit different. Instead of asking about sine of 30 degrees, it says cosine of 30 degrees. So we'll look at the 30-degree angle, and cosine would be adjacent over hypotenuse, which is just square root of 3 over 2. And again, if you look at sine of 60 degrees, from the 60-degree angle, sine would be opposite over hypotenuse, which again is square root of 3 over 2. Once again, we got the same value. And you can bet the same thing will happen if you look at tangent of 30 degrees and cotangent of 60 degrees. Tangent of 30 would be 1/2 over the square root of 3 over 2. So tangent of 30 is square root of 3 over 3. And if you look at cotangent of 60, from the 60-degree angle, cotangent would be adjacent over hypotenuse, 1/2 over the square root of 3 over 2. That's going to give us the same thing. So the tangent of 30 was the square root of 3 over 3, and the cotangent of 60 is going to be the same thing. Over here we would get just the square root of 3 for both of these answers. So all of these pairs of values have been the same. And if you look at the angles, the key is that these are complementary angles. 30 and 60 add up to 90, which makes them complementary. And the CO from the word complementary is actually where we get the names for sine and cosine, and tangent and cotangent, and like secant and cosecant. This is actually where our first set of identities comes from, these cofunction identities. Now it's a little weird how these are written out, but let me just explain where that comes from, this pi over 2 minus theta. First, remember that pi over 2 is the same thing as just 90 degrees. And remember that in any right triangle, and it doesn't have to be a special triangle anymore, that we could have some angle theta, and these 2 angles would add up to 90 degrees. And that's because all 3 of these add up to 180, but if this one's already 90, then we just get rid of that and we'll say that these 2 add up to 90 degrees. So if we're calling this angle theta, you could call this angle 90 degrees minus whatever theta is. And in that set of warm-up problems, we saw that if we take the sine of this angle theta, that would be like opposite over hypotenuse. That's the same thing as if you took the cosine of this angle, 90 minus theta, that would be adjacent over hypotenuse, and it's the same value. So sine of pi over 2 minus theta is the same thing as cosine of theta. Cosine of pi over 2 minus theta is the same thing as sine of theta. Tangent of this complementary angle would be the same thing as cotangent of the original angle, and so on. So just remember that for the cofunction identities, you just have to match up the functions and their cofunctions. With the quotient identities, you just want to be thinking like on the unit circle how we've been saying we could have this angle theta, and we've been saying that the sine value is the same thing as just the y value of that angle. So it's like this side of the triangle. Remember the key to that is the fact that the hypotenuse is always 1 on the unit circle. But the sine value is like the y value, and the x value is like the cosine value. And if you think of tangent being opposite over adjacent, that makes it sine over cosine. And since cotangent is the reciprocal of tangent, it's just cosine over sine. And speaking of reciprocals, we've been using these identities for quite a while. We know that sine is the reciprocal of cosecant, so I'm going to represent that by writing 1 over cosecant. Cosine and secant are reciprocals, so I'll write cosine as 1 over secant of theta, and tangent would be the reciprocal of cotangent. And notice how every time I write a trig function, I'm always writing an input with it. I'm always writing like cosine of theta. I never just write cosine over sine. And I know it's easy to just be lazy and fall into this habit, but don't write trig functions like that. Make sure you're always writing some kind of input like theta or x. We've also already seen even and odd identities. Back when we were graphing these things, we saw that sine and cosecant, tangent and cotangent all had 180-degree rotational symmetry, and that made them all odd functions. Whereas cosine and secant were even functions because they would flip on top of themselves if you flipped them horizontally. The way we write all this with identities is we say that the sine of the opposite of theta is the opposite of sine of theta. Cosecant of the opposite of theta is the opposite of cosecant of theta. So with odd functions, these identities basically allow us to take the negative outside of the parentheses and put it in front of the trig function. Tangent and cotangent were both also odd, so they have the same property. Cosine and secant were even, so for these we'd say that the cosine of the opposite of theta is the same thing as just cosine of theta, so the negative just kind of disappears. Secant of the opposite of theta is the same as secant of theta. For the Pythagorean identities, we're going to look at a right triangle on the unit circle again, and we're going to see how we can extend the Pythagorean theorem using what we know about trig. So with the Pythagorean theorem, you'd usually label this triangle as like A, B, and C being across from the right angle, and then you'd say that a squared plus b squared equals c squared. But now we're calling this leg of the right triangle like the sine value, and this side of the right triangle we're calling cosine. So I'm going to replace the a with sine of theta. Now it's kind of weird the way we write this. We won't say sine of theta squared because that looks like we're squaring theta, and what we really want to do is square sine, so it's going to be sine squared of theta. So sine squared is the function, and this would be the input. And that's just a weird notation thing you're going to have to get used to. But anyways, we'd have sine squared of theta plus cosine squared of theta. And for c squared, if you look at the triangle, this is on the unit circle, so again, c, the hypotenuse, is just 1. So this is just going to be 1 squared, which is just 1. And this is the first main Pythagorean identity. Sine squared plus cosine squared equals 1. And this is kind of the most important one because we're going to base all of the other Pythagorean identities off of this one. But I should back up a step and explain that the reason we have all of these identities is so that we can manipulate expressions later. So it's good to have more than just one version of the Pythagorean identity, sine squared plus cosine squared equals 1. So in this equation, I could subtract cosine squared over to the other side, and that would give me sine squared equals 1 minus cosine squared. Or going back to the first equation again, I could subtract sine squared over to the other side. So these are just 3 slightly different versions of the same identity. But of course we work with a lot more than just sine and cosine, so here's another trick that we can do. If I divide this entire equation by sine squared of theta, I would have to do that individually, like one piece at a time. So sine squared of theta divided by sine squared of theta is just 1, and then it says plus, so plus, and then cosine over sine is cotangent. So cosine squared over sine squared is just cotangent squared of theta. And then on the right side, 1 over sine, well, that's like the reciprocal of sine, which is cosecant. So now we have an entirely different looking Pythagorean identity. 1 plus cotangent squared equals cosecant squared. And to get to this row, all you have to do is divide by sine squared. So now I'm going to do the same thing. I'm just going to take this equation and rearrange it a little bit. So the first thing I'll do is just subtract cotangent squared from both sides. And that gets rid of this, so we just have 1 equals cosecant squared minus cotangent squared. Or instead of subtracting cotangent squared, I could subtract 1 from both sides. Now to get to the third row, we're just going to divide by cosine squared instead. So one at a time, if I took sine divided by cosine, that would be tangent. So this will start with tangent squared of theta. And then if I had cosine divided by cosine, that would just be 1. So tangent squared plus 1 equals, and then on the right side, if we have 1 over cosine of theta, that would be the reciprocal of cosine, which is secant. So secant squared of theta. And you can see that these two rows are actually pretty similar. They have cosecant or secant on the right side, and 1 plus cotangent or 1 plus tangent on the other side. But I'll fill out the last two by doing the same thing I did before. First I'll subtract 1 from both sides, and then for the other one I'll subtract tangent squared from both sides. So there's your list of the 9 Pythagorean identities. After all of that, we can finally look at 3 examples of using these identities to find trig values. The directions here say use the given function values and basic identities to find the indicated trig functions. And in the directions, it doesn't say to make right triangles and use opposite, adjacent, and hypotenuse sides. We have to use the identities. So these are just exercises to see if you can apply what you know. So they tell me that tangent of theta equals 3 and cosine of theta is 1 over the square root of 10. When I'm asked about cotangent of pi over 2 minus theta, if you look back at that identity, this was just the same thing as tangent of theta. And they told us the value of tangent of theta, that's just 3. So this just equals 3. For secant of theta, I think I'm going to use the reciprocal identity, because I know that secant and cosine are reciprocals. So if I know cosine is 1 over the square root of 10, the reciprocal of that would just be square root of 10 over 1, or just square root of 10. And same thing for cotangent. I know it's the reciprocal of tangent, so the reciprocal of 3 would just be 1 over 3. This last one's a little tricky. I'm going to show you 2 ways that you can find sine of theta here. First, I'll use a quotient identity. And this works out conveniently because I'm looking for sine, and the 2 values they told me were tangent and cosine. So I'll just replace those values in the equation, and now we just have to solve this for sine. So I'm just going to multiply both sides by this 1 over the square root of 10. And of course, 3 times 1 over the square root of 10 is just 3 over the square root of 10. And I'm not going to worry about rationalizing the denominator right now, just because that's not really the most important thing in this problem. So one way, we got 3 over the square root of 10. But you're not always given tangent and cosine together. So you could also use a Pythagorean identity. So if you remember sine squared plus cosine squared equals 1, I could just fill in the value for cosine, except remember we're squaring it. So it's going to be 1 over the square root of 10, that was the value of cosine, being squared now, equals 1. If you square this fraction, on top you just get 1, and on bottom you just get 10, because the square root of 10 squared is just 10. On the right side we still just have 1. So I can get sine squared alone by subtracting the 1/10 from both sides, and 1 minus 1/10 would be 9/10, and then I just have to take the square root of both sides to make this just say sine. So taking the square root of both sides gives me sine of theta equals, now the square root of 9 on top would be 3, but I can't really take the square root of 10, so I'll just leave it how it is. And notice we got the same value that we did before. It is worth noting, though, that when I take the square root here, technically I should get a plus or minus in front of this value. So then you have to choose, should you pick the positive or the negative one? And to do that, you just have to think about on the unit circle. I'm not going to draw a triangle here, but I just have to figure out what quadrant I'm in. So using the two values they gave me, tangent of theta is positive. That means I'd have to be in the first quadrant where everything's positive, or down here where tangent is again positive. But they also tell me cosine is positive, and that happens in the first and the fourth quadrants. And you can see these are overlapping in the first quadrant. And everything is positive there. Sine is definitely positive. So that's how I know I'd want to pick the positive value, and that's why we got positive 3 over the square root of 10 before. In this example, we're just given the value of cosecant of theta, which is negative 2. We don't know what tangent of theta actually equals, we just know that it's positive since it's greater than 0. So we can just follow the steps given here. So like part A says find the correct quadrant, and that's the same thing we just did in the last problem. So if I know cosecant is negative, that clues me into knowing that the sine of theta would also be negative, and I'm going to write that as just less than 0. So if sine of theta is negative, remember sine is a y value, that would happen in the bottom quadrants here, so 3 and 4. And if tangent is positive, that happens in the first and the third quadrant. So you can see these are overlapping in the third quadrant. So that information will come in handy in just a little bit. Next it says use a reciprocal identity. So if we're given cosecant, first of all I could fill that in right away. I know cosecant is negative 2. And I know the reciprocal of cosecant is sine. So the reciprocal of negative 2 would be negative 1/2. Next we're going to use that Pythagorean identity just like we did in the last one. So we have some options here. We could use the one with sine in it and that would give us cosine, or we could use the one with cosecant in it and that would actually give us cotangent. It doesn't really matter which one we use, but people are most familiar with the sine and cosine one, so I'll just do that one. So sine squared plus cosine squared equals 1, and I'm just going to fill in negative 1/2 for the sine value, but remember we have to square that. And squaring a negative makes it positive, so this would be positive 1 on top over 4. And if I'm trying to solve this for cosine, I'm just going to subtract 1/4 from both sides. So if you have 1 and you subtract 1/4, that leaves you with 3/4, and then we'll just take the square root of both sides. So on the left we have cosine of theta, but on the right technically we have plus or minus. On top I can't simplify square root of 3, so I'll leave that how it is, but on bottom square root of 4 is just 2. So this is making sense because 1/2 is a special triangle value that I'm used to seeing, and if sine is 1/2, it makes sense that cosine would be square root of 3 over 2. But I do have to figure out if it's positive or negative. And since we decided that we're in quadrant 3, the cosine value over there would be negative because remember cosine is an x value, and this is where we have negative x values. So I'm going to say that the cosine of theta is negative square root of 3 over 2. So then I can jump over and get the reciprocal value. That would be negative 2 over the square root of 3. And again, I'm not going to worry about rationalizing the denominator. The last one we need to get is tangent and cotangent. And for that, I'm going to use the fact that tangent is sine over cosine. So tangent of theta in this case would be negative 1/2 over negative square root of 3 over 2. So we'll think of that as multiplying by the reciprocal. And the negatives will cancel, the 2's will cancel, and I'm left with 1 over the square root of 3. And the reciprocal of that would just be square root of 3 over 1, which is just square root of 3. And finally, we have our last example. It's the same thing here, but they tell us that sine of theta is negative 1 and cotangent of theta is 0. So I'll fill in what I know. Sine of theta is negative 1 and cotangent is 0. And let's use those reciprocal identities right away. So if sine is negative 1, the reciprocal of negative 1, if you put it over 1, would just be 1 over negative 1, which is still just negative 1. And over here, 0, well, the reciprocal of 0, again, if you put this over 1, that would become 1 over 0, and you can't do that, so the tangent value would be undefined. So the only thing we have left is to figure out the cosine and secant values. I'm going to use sine squared plus cosine squared equals 1 again, because I can fill in -1 for sine, and that'll help me figure out cosine. So squaring -1 is just 1, and if you subtract that from both sides, you're going to get cosine squared just equaling 0. And if you take the square root of both sides then to get just cosine, the square root of 0 is just 0. Like, it's okay to take the square root of 0. So cosine of theta is just 0, and again the reciprocal of 0 is going to be undefined.